All right, we're going to start this lesson today with a warm-up. So if you would pause the video real quick, try the warm-up questions, and then hit play when you are ready. Okay, so here is my work for the two warm-up questions. I suggest you just pause your video for a moment to check your work, and then when you're ready, go ahead and move on. Okay, so we're going to be evaluating definite integrals today. And so definite integral just means that you're evaluating within a certain area. But all of these examples we're going to see are going to require that you use u substitution. So we're going to start with doing our u substitution. Everything is going to be very similar to what we have been working on in the first half of lesson 5.5. I went ahead and took my derivative and multiplied dx to the other side. Now this is where I kind of like to reevaluate, to see what I've got and what I need. So I know that all this is u. I still need something for dx. So I need to divide by the 5. And that tells me that dx is equal to negative 1/5 du. So here's my negative 1/5. I'm going to keep my integral. And this would actually end up being 1 over u squared du. Okay, I am going to rewrite 1 over u squared as u to the negative second power because it's easier to antiderive when you have an exponent given. And now I'm to the point where I can go ahead and do my antiderivative. So this would be add 1 to the power, divide by the power, and we are evaluating this from 1 to 2. Now in this next step, what I'm going to do is I'm going to do two things. I'm going to go ahead and clean this up, and I'm also going to change it from u's back to x's. Okay, so let me show you in baby steps here. But right now I have 1 over 5u, if I simplify. But I need to make that change back to the world of x's because my interval values from 1 to 2 are written in terms of x because that's how the original equation was written. Okay, so we have to change it back to in terms of the x variable in order for any of the work to be correct. So we are going to have 1 over 5 times 3 minus 5x. I think probably for me personally, it's going to be easier to distribute the 5 before I plug anything in. It's not required. That's just a personal preference. All right, so now that I have everything back into terms of x, I'm going to now plug in my numbers. Remember, you plug in 2 first. And then you plug in 1 and you subtract those values. Okay, simplifying is basically the only thing we have left. 15 minus 50, that would be negative 35. 15 minus 25, that is negative 10. Actually, I think instead of negative 10, I'm just going to make this a plus and make this a plus. We're going to need a common denominator, so I think I can multiply by 2 to make that 70 and multiply by 7 to make that 70. So that's going to be negative 2 over 70 plus 7 over 70, which gives us a final area measurement of 5 over 70. And actually that reduces to 1/14. So 1/14 is your answer. Okay, now, that's a lot of steps. I don't know that you can avoid steps in this problem so much, but there is a different manner in which you can approach your process. So everything up until this point right here is non-negotiable. It has to stay the same. But let me show you how the evaluating step might be done differently. So remember how I said that these interval values are written in terms of x? Well, what you can do is instead of changing the equation back to x variables, back to being in terms of x, you can change the intervals and put them in terms of u. Remember that you established this rule at the beginning. You established the rule that u is equal to 3 minus 5x. So these 1 and 2 values, you can also re-establish what they would be equal to in terms of u. Okay, so what you would do is you would say if x is 2, then I could plug 2 into this little equation and find what it would be in terms of u. So if x was 2, that would make this value 3 minus 10, which is negative 7. So instead of plugging in a 2, I can leave the equation in terms of the letter u and plug in negative 7 instead. Okay, let's try the other value. So the other value, take your u equation, plug in 1 for x, because this is an x value, and 3 minus 5 gives us negative 2. So instead of plugging in 1, I can plug negative 2 in to this equation that is in terms of the letter u. Okay, let's keep going and see how this looks. So it would be plug in negative 7 first, plug in negative 2, and look what happens. You get negative 1 over 35 minus, actually it would be a double negative, so plus 1/10. It's the same darn thing we had over here, right? Still would get a common denominator and all that jazz, but I don't know, I feel like the work is a little bit less if you take this approach, okay? It doesn't matter. Choose whichever technique you'd like. You know, take whichever method makes most sense to you, but the idea is you can put everything in terms of x like we did over here, or you can put everything in terms of u. It is your choice. Let me do another problem kind of the same way. I'm going to do it 2 times to show you again how that works. But remember, the beginning of this process is not going to be any different than normal. Okay, so this is an interesting question. Actually, I think before I start with choosing a u value, I think just to understand the problem better, I'm going to write it as ln x times 1 over x. Okay, so ln x times 1 over x is the same as this, right? I think this is going to help me a little bit with establishing what I want u to be. So it's not a traditional problem because the denominator, if I were to make that my u, then the derivative would be 1 and I would have nothing to do with this. Okay, so bear with me, watch. I'm going to make u into ln x. I'm going to take the derivative, which is 1 over x, and I'm going to multiply by dx. Sets you up perfectly. All of this over here is du, and then this becomes ln u. Okay? So this is from 1 to e. This would be ln u du. Okay, so far so good. Let's keep going with the antiderivative. Actually, not ln u, goodness. Just u, not ln u. Let's go with the antiderivative portion. So we're going to say the antiderivative of u is 1/2 u squared, and we are evaluating from 1 to e. So this is where I'm going to split, and I'm going to do the problem 2 different ways. So over here, I'm going to change the u back to x's. So that means instead of u, I put ln x. Everything else remains the same. We continue with this side, and we're going to plug in e. And then we're going to plug in 1. And we're going to evaluate. So let's see, 1/2 ln of e is 1. Ln of 1 is 0. So if you simplify, I believe this is just going to equal 1/2. Okay, option 2, let me go back to where we left off here with the black ink, and let me show you the other alternative. So the other alternative is you can leave the u values, or sorry, the u variable, but then that requires that you change the e and the 1 into terms of u as well. So remember, u is equal to ln of x in this problem. So if I want to change it, this is going to be, I'm going to plug in e, and I get 1. So that means I'm going to change this value to a 1 if I'm writing it in terms of u. Oops. And then I'm going to do the same thing down here. So plug it in, u is equal to ln of 1. That gives me u is equal to 0. So this value is a 0. And now I can continue the problem. So I'm going to plug in 1, and I'm going to plug in 0, and you still end up with 1/2. Okay, again, you can choose whichever technique you would like, turning it into variables using the x variable or using the u variable, it doesn't matter. Okay, last couple of things here. You know, we're always looking for tricks and ways that we can save time with our work, because calculus is obviously very tedious and time consuming. So let's make it easy whenever possible. So here's just a couple of things. These two little rules apply only to functions that are symmetric. Okay, so there's even functions and odd functions. So real quick review, even functions have y-axis symmetry. Odd functions have origin symmetry. So for even functions, think like parabolas. Odd functions, x cubed is a cubic function. That's a perfect example. Okay, so the theory is if you are in a situation where you want to know the antiderivative, so this is for A, you want to know the antiderivative of negative, let's say negative 5 to 5. So if this space is the same number over here, if your area is equal in size in both sides, okay? If you have an even function, which this one is an even function, this is what it could look like, the theory says what you could do is instead of evaluating from negative a to a, you could just evaluate from 0 to a and double your answer. The reason for that is that this is symmetric, so the area on the left is the same as the area on the right, so you would just find one of those areas and double it to get the total. Okay, the second integral for symmetric functions is for an odd function. So let's say we're in the same scenario and we want to go from negative 5 to 5 for some odd function. Odd functions have origin symmetry. So if your odd function is down in quadrant 3 on this side, then it would be up in quadrant 1 on the right side of the graph. They go right through the origin. If you look, these two area spaces are the same size, but one is below the x-axis and the other is above. So if this area is equal to negative 3 and this area is equal to 3, the total would still be 0, right? So again, this is just a trick, a little property, if you will, that helps you to evaluate integrals for even and odd functions a little bit faster than what you are used to. Okay, so here's an example. If f of x is equal to x to the 6th plus 1, it satisfies f of negative x equals f of x. Basically, this is just the definition that says that it is an even function. So if it's an even function, it's going to have a scenario kind of like this first picture where the left side is equal to the right side. It's symmetric. So what would be the area from negative 2 to 2? Okay, so we have a little bit of work to do, but what we can do to save time is we can say that the area from negative 2 to 2 would just be double the area from 0 to 2. Okay, It's a little bit easier to do 0 to 2 than it is -2 to 2 because you're plugging now a 0 in, which makes your life a lot easier as far as, your work. Okay, we're going to do an antiderivative. So add 1 to the power, divide by the power. And then this would be the antiderivative of 1 is x, but I threw the 2 there with it. And we are evaluating from 0 to 2. We plug in 2 first. And then we plug in 0. And we solve. Now remember the doubling value, I've already kind of run it through the problem, so I already know what that's going to be. This is going to be 2/7 times 2 to the 7th power, I think is 128, plus 4, and then these equal 0, so actually we could just get rid of that. And then the final answer is going to be, we get a common denominator, it's going to be 284/7. Okay, last problem. So this one here, the directions say that tangent of x over 1 plus x squared plus x to the 4th satisfies f of -x equals a negative f of x. Again, that's a definition that describes an odd function, so it just means it's an odd function. Remember, an odd function has origin symmetry like this one here, okay? So remember, the areas kind of cancel each other out if they're the same size on each side. All right, so if I am asked to find the area from -1 to 1, and I know that it's an odd function, then I can guarantee it's going to look kind of like this, and the areas are going to cancel each other out. So there is no work required, and you can just say that the area is equal to 0. Okay, you have another circuit. I'm going to be getting back to you with help on a few of those questions in the circuit. So make sure that you look in the homework post for more information on that assignment.